You want to buy a tokenized real world asset, a piece of real estate, a bond, a share in a fund. And before you can touch it, the platform needs to verify your identity. That makes sense, right? It's regulated. So you hand over your passport, your nationality, your date of birth. You prove you have enough money. This is standard KYC. And here's the problem. On Ethereum, for example, that verification either lives in a centralized database, one breach away from exposing every investor, or it gets reduced to a public whitelist where your address is forever linked to this person's past KYC. Either way, you've leaked information that can never be unleaked. So, now imagine doing the same verification, passport nationality check, wealth check, but where the blockchain never sees your passport data, never sees your name, never even stores your nationality. All it knows is this person proof they qualify, and the proof is mathematically unbreakable. That's what Brick Towers built with their Midnight real-world asset system on Midnight, and the cryptography that makes it work is genuinely elegant. Let's break it together. Before we get to the circuits, we need to understand what we are working with. And what we are working with is a passport. Specifically, the machine-readable zone, the MRC, those two lines of text at the bottom of your passport data page. If you've ever looked closely, it's a standardized format defined by ICAO document. Every country uses it. Every passport has the same fields in the same position. The Brick Tower system maps this MRC into a compact data structure called passport data. 14 fields covering both MRC lines: document code, issuing organization, holder name, document number, nationality, date of birth, sex, expiry date, for example. Check digits for validation, and personal number fields. And here's what matters for CK. Every single one of these fields is stored as a field type. That's pretty much a big int, a number that lives in the finite field of BLS 12381. And why is that? Because CK circuits do arithmetic. They add, multiply, compare. They don't manipulate strings. So your name, your nationality, your date of birth, all of it gets encoded as numbers that the circuit can compute over later on. This isn't just a data mapping exercise. It's a foundation of the entire privacy model. Once your passport is a collection of field elements, the CK circuit can selectively verify individual fields. Check your nationality without touching your name. Verify your age without revealing your date of birth, because each field is an independent arithmetic value. The circuit picks what it needs. Everything else stays dark. Okay, so you've got a passport data encoded as field types, but there's a problem, a big one. Government identity documents are signed with Edda on the P256 curve. That's the standard. Every government that issues digital passport uses P256 or a closed variant. And P256 is absolutely terrible for CK circuits. Verifying a P256 signature, for example, inside a CK proof would cost millions of constraints. It's computationally brutal. The circuit would be enormous. The proof generation would take forever, and it would be completely impractical. So Brick Towers built a bridge, the Identity API. Here is how it works. Here's the flow. The investor's passport has a government-issued P256 signature. The Identity API receives this signature and verifies that signature using a standard elliptic curve cryptography. The function government signature verifier TS handles this in plain TypeScript. No CK involved, just classical crypto. So you verify the government's signature is valid. Once that is verified, the identity API reassigns the credential data onto the JubJub curve using a trusted identity provider key. JubJub is an embedded curve inside BLS 12381, the curve that Midnight CK proof already operates on. So, verifying a signature on JubJub inside a CK circuit is cheap. Hundreds of constraints instead of millions. So, the resigning uses generate deterministic key and compute challenge for credentials. These are functions used within the repo of this code. These are functions that mirror the exact circuit logic from the compact contract. The off-chain TypeScript and the on-chain CK circuit compute the same math. This is critical. If they compute differently, the circuit would fail on-chain. Okay, so the identity API exposes a single HTTP post endpoint, sign. The passport data goes in and JubJub signed credentials comes out. That signed credential is what the investor submits to the blockchain. The government's P256 signature never needs to enter the CK circuit at all. So the pattern works this way. Verify with one curve off-chain, resigns onto a CK-friendly curve. Verify that signature on-chain. So this is how it's going to become a standard infrastructure for any system that bridges government identity into CK. Remember where you heard that first. The signature scheme itself is a Schnorr-like construction defining crypto.compact. And if you understand Schnorr signatures, you will recognize the structure immediately. If you don't, this is your crash course. The sign function takes a credential and a secret key. Step 1. Compute the public key. PK equals G times CK, circuit key, where G is the JubJub generator point and CK is the secret key. A standard elliptic curve scalar multiplication. Okay, step 2. Compute a deterministic nonce. K equals hash of the secret key and the credential. This is the deterministic K function. And deterministic, it's the key word here. In classic Schnorr, if you ever reuse a nonce with a different message, an attacker can extract your secret key. Game over. By deriving K from the secret key and the credential, you guarantee a unique K for every credential. Same credential, same K. Different credential, different K. No reuse, no extraction. Okay, let's go to step 3. Compute the commitment R equals G times K, another scalar multiplication. This R value is public. It will be part of the signature itself. Okay, let's go to step 4. Compute the challenge. C equals hash of R, which is the commitment, PK public key, and the hash of the credential. Notice the double hashing that we have here. The credential gets hashed first via compute challenge. Then that hash joins R and PK in the final challenge computation. This is the Fiat-Shamir transform. It makes the interactive Schnorr protocol non-interactive by replacing the verifier's random challenge with a hash. Step 5. Compute the response. S equals K plus C times CK. Addition and multiplication in the JubJub scalar field. The signature is the tuple R, S, pub key, C, packed as a challenge extract. Verification is one question. G times S equals R times pub key times C. If it holds, the signature is valid. If it doesn't, the credential was tampered with or signer doesn't hold the secret key. This is the entire verification process where the scalar multiplications, the points additions, and the comparisons take place. This runs inside the CK circuit. Every investor's identity, this identity checks produces a proof that these equations held without revealing any private information as the secret key. And it doesn't reveal any credential contents and without revealing any identity provider signed it. Well, except that the circuit does check that the provider's public key actually holds in another contract. We're gonna see that in a minute. Now we zoom out to the main event, the onboard function. This is the circuit that an investor calls to get authorized for real-world asset investment. It takes three inputs: a quiz, an input coin, and an identity. Think of it as a three parallel verification gates that all have to pass. Gate 1, the quiz. The investor answers a knowledge quiz about the asset or platform. The circuit computes persistent commitment quiz and stores the commitment. This proves the investor completed the quiz without storing the answers on chain. It's a compliance checkbox. Investors demonstrated understanding without recording what they actually said. Okay, gate 2, identity verification. This is the assert identity function. This is the big one. We'll break it down in the next scene, but at high level, it verifies the JubJub signature on the passport credential, checks that the signer is the trusted identity provider, and confirms the investor's nationality is on the allowed list. If all checks pass, the investor's public key gets inserted into the authorizations Merkle tree. A Merkle tree of C-swap coin public key values. This tree is the investor registry. If your key is in the tree, you are authorized. Okay, let's go to gate 3, wealth verification. We're going to use assert coin value input coin function, which checks that the investor holds sufficient assets. Specifically, the coin must be TBTC, checked by color, and the value must be at least 100 units. We'll dig into the mechanics in scene 7. All three gates are enforced in a single CK proof. One transaction, one proof generation, the chain sees quiz commitment stored, investor key added to the authorization tree, and the wealth verified. The chain does not see quiz answers, passport data, investor name, date of birth, document number, or actual wealth amount beyond the minimum threshold. Okay, and notice the sealed ledger variables at the top of the contract. For example, the identity provider, public key, the TBTC coin color, allowed country codes. These are set at deployment and never change. Let's unpack assert identity, because this is where the CK design decisions get sharp. First, signature verification. The circuit extracts the challenge struct from the identity input and calls verify credential challenge. This runs the Schnorr verification equation we covered. If the math doesn't check out, the whole transaction fails. No valid signature, no onboarding. Second, trusted provider check. The circuit reads challenge pub key, the public key of whoever signed the credential, and compares it against the identity provider public key from the sealed ledger state. If they don't match, the transaction fails. This is the trust anchor. The contract only accepts credentials signed by the specific identity provider that was configured at deployment. Third, and this is the most interesting part, nationality verification. The circuit calls disclose identity. That word disclose is loaded. It means the nationality value leaves the privacy boundary and can be used within the circuits. After all these three checks pass, the investor's authorization gets inserted into the authorizations Merkle tree via push. They are now in the registry. They can participate in the real-world assets market, and the only thing the chain recorded is the Merkle tree insertion and the validated proof. The wealth check is clever in its simplicity. As a coin value takes an input coin, a C-swap coin, and runs two checks. First, the coin color. The circuit compares input coin's color against the sealed TBTC coin color. This ensures the investor is proving wealth in the right assets. You can't pass off some random token as TBTC. The color is a cryptographic identifier backed into the coin, and the check is exact equality. Second, the minimum value. The circuit asserts that input coin value is greater than or equal to 100. This is the wealth threshold. You must hold at least 100 TBTC to qualify. But here's the pattern that's subtle. The coin is temporarily deposited into the contract and then immediately returned. It's a proof of possession, not a payment. The coin enters the circuit, gets verified, and leaves. The investor doesn't lose anything. They just prove they have the required balance. Why this works? C-swap coins on Midnight are private by default. The coin's value and color are hidden, but inside the CK circuit, the coin is open, the circuit can read the value and color, perform the checks, and generate that proof that checks that something passed. The actual value does not leave the circuit. An observer knows the investor met a threshold. They don't know if the investor holds 100 TBTC or 10,000 TBTC. The minimum is verified, the actual amount stays always private.